Hi, welcome to the video solution for Edexcel IAL Physics. This is October 2019, third video for the series for Unit 2. So let's start. Question number 18. When an incident ray of light meets a boundary between air and glass, some of the light is reflected and some is refracted as shown. Okay, so this is diagram. We have two mediums, air and glass, and the light is coming. This is incident ray. Definitely the incident ray would be unpolarized light, and point of incidence, some part of the light is reflected, some is refracted. The reflected light is partially plane polarized. What is meant by plane polarized light? So remember, what are they saying? We have incident ray. This is unpolarized. Unpolarized means this is oscillation. This is oscillating in many planes, horizontal and many planes, something like this. And there are many planes that you can keep thinking. So this is unpolarized light. And when it is reflected, and they are saying in the question, the reflected light is partially plane polarized. So this is plane polarized, not completely, but partially. So this is a plane polarized, and we need to define state what is meant by plane polarized light. A typical definition of a plane polarized, that the oscillation in one plane, that means if we have oscillation in a vertical plane, and this oscillation is perpendicular to the direction of motion. So you can say that oscillation is up and down, and direction of travel is horizontal. So we say that we have a light is plane polarized light. So 2 points for 2 marks. Oscillation in one plane that is perpendicular to the direction of travel or direction of motion. So that's how you can write definition of plane polarized light. Part B, deduce whether the refracted ray is unpolarized or partially plane polarized light. So if you see the diagram and if you see the part A, in which they say that the reflected ray is partially, it is partially plane polarized. It is given, it is partially plane polarized. Now what does it mean? What is happening? Suppose this is incident ray, and incident ray is clearly unpolarized. That means we have vertical plane, we have horizontal plane oscillation, we have some other plane, and you can draw many other planes. Infinite number of planes are there, unpolarized light. Now what is happening here in at point of incident? In point of At point of incidence, some light is reflecting and some is refracting, and they are saying that the light which is being reflected, this is partially plane polarized, meaning some of the plane is reflecting. Let's suppose, if I say, if it's just an assumption that I assume that we have just these maybe maybe one, two, three, or four planes. So plane number one vertical, plane number two, plane number three, and plane number four. Now what happened? What is the meaning of partial plane? Meaning some of the plane is reflecting. So I assume that only horizontal plane, and which is plane number 3, and plane number 4, suppose plane number 4 is reflecting. So this is called partially plane polarized light. So what about the rest of the other plane, like plane number 1 and 2? Definitely they will be refracting. So plane number 1 and plane number 2, they will be refracting. So if reflected ray is partially plane polarized, that means the refracted ray must be partially plane polarized light. That's how you can visualize the situation. And now you can write your answer like this. So the reflected ray is partially plane polarized as given part A. There must be some oscillation in refracted rays which will be perpendicular or penetrating or transmitting into the other medium. So refracted ray should be partially plane polarized. At the Brewster angles theta b, the reflected light is completely plane polarized. This occurs when the reflected ray and the refracted ray are at right angles to each other, so that theta b plus r is equal to 90 degrees. So if reflected and refracted ray are at a 90 degree, then at that moment the incident angle is called Brewster angle theta b, and at this condition the refracted ray or the reflected ray are completely plane polarized. The reflected one is completely plane polarized. So show that tangent theta b is equal to Ng over Na, where Na is the refractive index of air and Ng is refractive index of the glass. So we need to drive this equation according to given condition. And we know that because we are dealing with refractive index. And what do we know about the refractive index relation with the angles? We know that we have a relation of refractive index of two mediums with the angle. So n1 sine theta 1 is equal to n2 sine theta 2. So we are going to use this equation or this relation for our given conditions or for our given medium. Remember, this is air with refractive index of Na, and this is second medium glass of refractive index G, and this is our theta 1 in the first medium, and this is our theta 2. So if I apply the given condition uh, for our given medium, so I can say that Na sine of theta b is equal to Ng sine of r, which is theta 2. Now if you see in our given or required proof, we need theta b, Ng and Na. We don't need this r, so we'll have to get rid of this r. And how do we do that? We are given this relation theta b plus r is equal to 90. That means r is equal to 90 minus theta b. I can replace r with 90 minus theta b. So now my new situation will be Na sine theta b is equal to Ng sine r, and r is 90 minus theta, which is angle 90 minus theta b. Bracket close. This whole thing is angle. Now those who are studying maths, you have studied a formula in trigonometry that if you have a sine of 90 minus x, if you have sine 90 minus x, it is equal to cos of x. Or if you have cos 90 minus x, you can write it as sine x. So sine 90 minus x is cos x, or cos 90 minus x is sine x. This is a kind of a formula in trigonometry. So because I have sine 90 minus theta b, so I can write Na sine of theta b is equal to Ng sine 90 minus theta b can be written as cos theta b. So why we are converting this sine into cos? Because we need theta, and we know that in maths that sine x divided by cos x is equal to tangent x. So that's why we include cos in our equation. Now you just rearrange, or you send cos theta on the other side and bring NA on the right side. So you can rearrange this whole equation as sine theta b divided by cos theta b is coming on the left hand side. So in denominator, cos theta b is equal to, on the right hand side, Ng divided by Na is coming on the right hand side, so Na. So sine over cos becomes tangent theta. So tangent theta b is equal to Ng over Na. Hence proved. This is our required derivation. So these are just for your reference, and I did in detail. You can skip some of the step if you are okay with these. Calculate theta b. So now calculate theta b for the light passing from air into glass. So Na, this is Na, and this is Ng. So tangent theta b is equal to Ng 1.5 divided by 1, Ng upon Na from previous part. And if you solve this equation for tangent theta, so tangent theta b would be equal to tangent inverse 1.5. So theta b is 56.3 degree, or you round it off to 56 degree. This is the angle theta b. Different colors of visible light are refracted as they pass through a prism as shown. This is the dispersion process. White light is splitting into its component and making, the 7-color rainbow with Geor or Roy Bev. So students suggest that the Brewster angle for violet light would be smaller than for the red light, as violet is refracted more than the red. Criticize this suggestion. So if you see what is happening here, you are given a relation tangent theta b is equal to Ng over Na. If you rearrange for Ng, so Ng would be equal to Na tangent theta b. Now if you see what is happening, red light and violet light, if you compare, red light is refracting less and violet is refracting more. So because violet light is refracting more, that means for violet light the refractive index of glass is more. That means for violet light, value of Ng is greater. So that's the idea. Now see what is happening. If you have a two different light, like ray 1 or something, like you see like something like this is ray 1 and ray 2, both are coming parallel but two different color, and you observe this is the normal line, this is the normal line, medium 1 and medium 2. And if you observe that the ray 1 is refracting something like this and ray 2 is refracting something like this, so we have a same medium but two different light is bending or refracting with different angle, less angle, more angle, refracting angle is more. Then why it is happening? Because for the second ray, the refractive index of the second material is more. So if you say that if the refractive index of material medium 2 is n2, that means refracting index for ray 2 is more. That's why it is bending or it is refracting more, so with greater angle. So here violet is refracting more. That means for violet light, Ng is greater. Now, if you see the relation, Ng is greater, it is only possible if theta b is higher, not smaller. Because as theta increase, then tangent value of theta is increased. Like if you compare tangent 30 and tangent 45. So theta is increasing, so overall value of tangent is increased. That's why angle of refractive index is increased. So that's how you can compare the Brewster angle or theta b with reference to the refractive index. 19. A loudspeaker produces a sound wave in air. Diagram 1 shows air molecule before the sound wave passes. Diagram 1, so this is without any sound waves in a normal displacement. At particular instant, this as the sound wave passes, the air molecules are displaced as shown in diagram 2. So now the sound wave is passing as a compressional waves or a longitudinal waves. Label a point on diagram 2 where the pressure of the air is minimum. So pressure is minimum at rarefaction. Rarefaction. So if the particles are further apart, this is called rarefaction. So you can see this is diagram 2, label a point. So you can label the point like this. Uh, this is the refraction, or you can mark here any of the position, but it should be in a rarefaction situation. So if you mark this, or you can mark this is the rarefaction, or you can mark on a point, it's fine. So at rarefaction you have a minimum pressure. At compression, of course, you have a high pressure. So these are the points of minimum or low pressure. Sketch a graph of displacement against distance for the air particles between A and B at this instant on the axis below. So you have the given diagram 2. So you need to sketch the displacement time graph corresponding to this position. Now if you see what is happening, if you compare for a transverse wave, something like this is crust, trough, crust, trough. So you can imagine that the compression and rarefaction corresponds to this crust trough, crust trough. So alternate crust trough, crust trough, compression, rarefaction, compression, rarefaction, compression. So from one crust to another crust you have one wave. So one crust and then crust and then another crust. So what do you think? How many wave? One and then two. So you have a compression, another compression, another compression. So you have a two compression. That means you have two complete waves. So compression, rarefaction, compression, rarefaction, and then compression. So you need to make two complete waves from A to B, not just one. And it's your choice whether you can start with minimum or maximum, but make sure that when you plot the graph you sketch two complete waves. So you can say that, let's suppose starting from here, and this is just for your understanding, this is for your here, another compression, this is the rarefaction, and their compression is at B. So you need to make two waves till B, complete waves. So from this C to this C, there should be one wave. So you can imagine something like this. So this wave should be, coming to the point B. So something like this. With equal amplitude. So that's how you need to plot. And if you wish, you can flip. Instead, you can draw something like this. This is also acceptable. So both are fine because they are not giving you any phase, whether phase is inverted or they are just saying sketch. So both are acceptable, either blue or red. But there must be two waves because of compression to third compression. Part B. The speed of sound can be determined using the apparatus shown. So this is the apparatus, two beam oscilloscope, signal generator, loudspeaker, meter rule, and microphone. When the loudspeaker is switched on, two traces are produced on the oscilloscope, one directly from the signal generator and the other from the microphone. Describe how a value for the speed of sound in air can be determined. So what to do to find the speed of sound using these arrangement? So we have a two beam oscilloscope connected with this instrument. Now you can imagine what is happening. This oscilloscope is showing basically two signals, one directly from frequency generator. So this is the direct signal from frequency generator, and the second signal is we are receiving on the screen. The loudspeaker is producing sound and traveling, receiving in a microphone, and microphone sends signal to the oscilloscope. So we receive second signal from the microphone. So what is happening, or how do we do that? We start our experiment by fixing the position of microphone and the speaker. So we note down the position of the microphone, and initially we need to adjust the position so that both the signal have either same phase or in anti-phase, meaning both signal would be something like this or like this. So these are in phase, or maybe you can imagine you can adjust one and then other, something like this. So they are in anti-phase. So you can adjust the position of microphone and speaker so that the initially both of the signal will either be in phase or an out of phase, and you note down the distance from the meter rule. So once you note down the position and you set the uh, phase and anti-phase position, and then you start moving microphone or speaker, either one of these. The easiest one is microphone. So microphone you move toward the speaker, and as soon as you move the microphone toward the speaker, you see that the wave will not remain in phase. So they will be out of phase. So you will be seeing, looking at that the wave is moving rightward or the leftward. So they will be not in phase. So there will be something like this, and you keep moving until you receive the second phase or antiphase condition. And suppose the microphone reaches here, and at this position you find this second phase or antiphase overlapping of the two signals, and then you note down the position and the distance traveled by the microphone. In fact, this distance traveled by the microphone will be equal to the wavelength of the sound produced. So distance corresponds to the wavelength because you got just next phase or anti-phase situation. That means the microphone has moved equal to the wavelength. This distance is lambda, and frequency can be measured from the frequency generator. So lambda multiplied by frequency will give you a speed. That's how you can find the speed of the sound. Describe how the oscilloscope display can be used to demonstrate that the two traces have the same frequency. Clearly, you know that oscilloscope horizontal axis is basically shows the time axis. Always in oscilloscope, horizontal axis is the time axis, so you can say that the number of waves generated divided by the time on axis, you can have a time period, and the reciprocal of time period is frequency. So if frequency is same, that means they if they have a same time period, so they must have a same frequency. A frequency of 15 kilohertz was used. A student suggested that experiment would give a more accurate result for a speed of sound. A frequency of 4 kilohertz was used. Evaluate the student's suggestion. You should use a calculation in your answer. Speed of sound in air is 340 meter per second. So what do? We are given a speed and we are given frequencies. So the idea is using this velocity and frequency, we are going to figure out the wavelength corresponding to these values. So lambda 1 and the lambda 2 for the other frequency. So f1 and suggested f2. And then we know that this lambda 1 and this lambda 2 is basically corresponds to the distance traveled by the microphone d1. That's what the idea is, and looking at the value of the d1, then we can give the suggestion, or we can evaluate the student suggestion. So let's find lambda 1 or lambda 2, or you can say d1 and d2. So you know that the v is equal to f lambda. So lambda is equal to v by f. So lambda 1 is basically 340 divided by 15 kilohertz, so 15,000, and it will give you 0.023 meter, or you can say 2.3 centimeter. It's just to give you an idea. And for D2, 340 divided by 4,000, it will give you 0.085 meter, or 8.5 centimeter. Clearly, for D2 or for lambda 2, you have a higher value of distance traveled. That means for lambda 2, or you can say D2 at 4,000 hertz, you have a less percentage uncertainty. Less percentage uncertainty. So if less percentage uncertainty is less, then definitely you would have a more accurate value. So of course, a student suggestion is correct. We should use 4,000 hertz. Thank you very much. Have a nice time.